Hello and welcome to another CNCM lecture on generating functions. That's what we'll be discussing today. And so generating functions is basically a powerful accounting tool utilizing polynomials to help us count certain things. So let's move on. Well, so what are generating functions? Generating functions are a powerful tool that can represent probability with a polynomial. So a generating function usually has an exponent on the variable x, which is a state, and the coefficient of that x to the k is the probability that that state is achieved. And this is best explained with an example. So let's go on. So if you look at a dice roll using generating functions, and the generating function for the roll of one standard die is represented by this generating function right here. As you can see, we have an equal probability of rolling any one of the six numbers, hence the probability of 1/6 on each of these. And our exponents are the states. We can roll a 1 with probability of 1/6, we can roll a 2 with probability of 1/6, and so on. And this is our generating function for the probability of what we can roll on one standard die. So yes, the exponents of x are the states that we can achieve, and the coefficients of x are the probabilities of each achieving each state. And in this case, the states are what number we roll, and the probability is the probability of rolling that number. So now we can use this to solve a problem. So we want to find the number of possible ways to roll the sum of 5 on two standard dice. To do this, we multiply the generating functions of both dice, which gives us 1/6 x plus 1/6 x squared, so on squared. But we can make this simpler by factoring out a 1/6 squared, giving us 1 over 36 times this polynomial right here, which is much nicer for us when we were calculating. So moving on. We wish to find the coefficient of x to the fifth, as that corresponds to the state of 5 being rolled as the sum of the two dice. Through expanding, we find that the coefficient which corresponds to our probability is 4 over 36 equals 1/9. If you expand this polynomial, you will get that the coefficient of x to the fifth is 4 over 36. Now, to kind of understand why this works, well, let's say we rolled an x cubed on the first dice, which corresponds to a 3, and an x squared on the second dice, which corresponds to a 2. Well, this clearly sums to 5. Well, if we take the product of these two variables, we get x to the fifth. This is why this works. Since we're multiplying these two variables, the exponents add, giving us x to the fifth. And hence, the number of ways we can get 3 and the number of ways we can get 2, they get multiplied to give us the number of ways we can get 5. So, if you think about this logically, how many ways are there for us to roll 5 on a dice? You can see that there's 3, 2, 2, 3, 4, 1, and 1, 4. So our generating function is correct. 4 over 36 equals 1/9. So this multiplication that leads to exponent addition is why generating function is so powerful. It helps us for problems where we usually take sums, and we'll learn more about that as we go on in this lecture. So let's actually cover a concrete problem so we actually get an idea for how generating functions work. So this is the 2010 AME 1 number 4, and it says that Jackie and Phil have two fair coins and a third coin that comes up heads with probability 4/7. Jackie flips 3 coins and then Phil flips the 3 coins. Let M over N be the probability that Jackie gets the same number of heads as Phil, where M and N are relatively prime positive integers. Find M plus N. So let's find the generating function for these coins. And we're going to put it in terms of heads because you're trying to calculate what's the probability that they get the same number of heads. So we want to calculate how many ways there are to get X number of heads. So in a fair coin, obviously, we either get tails, which doesn't contribute to our count of heads. So it just contributes 0, which is X to the 0, which equals 1. Or we could flip heads, which happens with probability 1/2. I forgot to state that too. This happens with probability 1/2. And we can roll flip heads with probability 1/2. and that corresponds to x to the 1 because that is adding to our count of heads. Now we can square this since there's two of these fair coins, and there's a third coin that comes up with heads with a probability of 4/7. Well, we roll tails with a probability of 3/7, and we roll heads with a probability of 4/7. And so we add to our count of heads if we roll heads, and that happens with a probability of 4/7. Now to make this much cleaner for ourselves, we can factor out the fractions. We can factor out 1/2 squared from this side and 1/7 from here, and we get that this is equal to 1/28 of 1 plus x squared times 3 plus 4x. Now, this gives us a probability distribution of getting some certain number of heads when we flip these three coins. And this is only for one person. So let's look at the probability, and I'll put the expansion up here. It's fairly easy, but I'll just write it out on my piece of paper here and write it up as it would take a lot of time to actually write it on the board. So I'll do that real quick. And if you actually expand out this polynomial, you will get that this is equal to 1/28 times 4x cubed plus 11x squared plus 10x plus 3. And so this is the probability distribution of flipping k number of heads when we flip these three coins. This 3 corresponds to the number of ways you can flip 3 heads, which is 4/28 is the probability. 11 ways to flip 2 heads, 10 ways to flip 1 head, and 3 ways to flip 0 heads. So let's continue on with this. Moving on. We actually want to convert this problem. Now, the whole point of doing this was to find out what the probabilities were of rolling k number of heads. Now, with basic counting principles here, we know that for them to roll the same number of heads, they both must roll the same number of heads, obviously. So we have some cases here where Phil and Jackie either roll 0 heads, which happens with probability 3/28, and we have to square it since they both have to flip 0 heads. And we keep on doing this, and we get 4 squared over 28 squared, and so on. 11 squared over 28 squared plus... And that's with... Okay, let me clear that up, actually. So let's just go from left to right. So the probability that they both flip 3 heads is a probability that Jackie flips 3 heads, which is 4/28, and that Phil flips 3 heads, which is 4/28, so we square them. So 4/28 squared. And then with 2 heads, it's 11/28 squared. And with 1 head, it's 10/28 squared. And with 0 heads, it's 3/28 squared. All right. So we just have to compute this value, and that'll give us our answer. So this is 4 squared plus 11 squared plus 10 squared plus 3 squared all over 28 squared. 28 squared is 784, and the rest of the squares are just 16 plus 121 plus 100 plus 9 all over 784. This gives us 137, 237, 246 over 784. And we can simplify this down to 1, 2, 3 over 3, 9, 2. And that's the simplest form of this fraction. So we just have to add these two up, as the problem states that we just have to find up n plus n. So we just add these two up. We get 1, 2, 3, 3, 9, 2. Adding these up gives you 5, well, 515. And that is your answer. And so we just went over an example of generating functions. We use generating functions to represent the outcomes of flipping those three coins with one unfair coin. And then we just carried on with normal counting principles to find our answer. So moving on, let's cover the power series. This may seem like a new term to you, but it'll make sense as we go through this. So the generating functions that we have been working with so far have been finite, as in they only have like a few number of terms. But what if you had an infinite number of terms? If you want to represent a quantity with an infinite amount of states. If you could do so with an infinite polynomial, such as this, 1 plus x squared plus x cubed plus x to the fourth, and so on. It goes on towards infinity. And with this thing, this in fact can represent an integer when summing integers. So let me clarify that by an example. Say we wanted to find the number of non-negative solutions, a, b, c, d, of a plus b plus c plus d equals 3. We can represent each of a, b, c, d with the above polynomial. Since a, b, c, d, they can take on any integer value, non-negative integer value that is. So based on what we've learned about generating functions, our answer would just be the coefficient of x cubed, because that's the sum we're looking for, and the expansion of that whole polynomial to the fourth power. Well, with this, even though it's infinite, we could evaluate this logically, since there are only a very few combinations that multiply to x cubed. The combinations are... Let me get my mouse for a second. Okay, there we are. So the combinations are 1 times x cubed, x times x squared. Those are the only two combinations that multiply up to x cubed. And we could calculate this by hand since we don't have to consider all the terms past x to the fourth and so on. But this is possible since 3 is a very low number. What if we had a much larger number? That is, what if we had to deal with a number much larger than 3? This is where the power series comes into play. By the geometric series formula, the closed form for our infinite polynomial is shown below. 1 plus x squared plus x cubed plus x to the fourth is equal to 1 over 1 minus x. This is true by the geometric series formula, and you'll learn more about this in calculus. So which means we can represent our problem with the polynomial 1 over 1 minus x to the fourth. This is much simpler, but before we go on, there's powers of x in the denominator, and well, that's hard to calculate. But there is a negative binomial theorem, just an extension of the binomial theorem to negative exponents, since this thing right here can be written as 1 minus x to the negative fourth. And that yields that the coefficients of an expansion of 1 over 1 minus x to the nth power is equal to the sum from 0 to infinity of n plus k plus 1, n plus k minus 1, choose k, times x to the k. Well, basically what this is telling us is that this formula states that the coefficient of x to the k is n plus k minus 1 over k. Well, n plus k minus 1 choose k. Sorry about that. So revisiting our problem of the number of non-negative solutions a, b, c, d of the a plus b plus c plus d equals 10 equation, we get that our answer is the coefficient of x to the 10th in the expansion of 1 over 1 minus x to the fourth, as we said before. Well, using our generalization, this is just 4 plus 10 minus 1 choose 10, since n is equal to 4, since that's the exponent on 1 over 1 minus x, and 10 is the exponent that we were looking for. So our answer is just 4 plus 10 minus 1 choose 10, which is 13 choose 10. And if you use stars and bars, this is consistent with stars and bars, of course. Moving on. Find the number of positive integer solutions a, b, c, d to a plus b plus c plus d equals 10. This is a practice problem, and well, this might seem like the same thing we just did last time. However, there's a different condition. Instead of non-negative, we have positive. Why do we have that? Well, now we can't have x to the 0, which corresponds to the state of 0 in our expansion. In fact, we must have x plus x squared plus x cubed, and so on. And since we have 4 variables, we take this to the fourth. Well, we know that the closed form for 1 plus x squared and so on to the fourth is 1 over 1 minus x to the fourth. So let's just factor out an x from here. Since it's being taken to the fourth power, we factor out an x to the fourth, and that gives us 1 plus x squared, so on to the fourth power. Now we know the closed form for this, that's just 1 over 1 minus x, so we get x to the fourth over 1 minus x to the fourth is our closed form. Well, let's remove the x to the fourth for a second. You want to get to the sum of 10, so we want to find the coefficient of x to the 10th. Since you already have an x to the fourth here, we can just find the coefficient of x to the sixth in the expansion 1 over 1 minus x to the fourth. That's just subtraction and removing the x to the fourth here. So here we know how to do this. We have our generalization n plus k minus 1 choose k. So n in this case, which is the exponent we're taking, is 4. We want to find the sum of the coefficient of the term x to the sixth, so we go plus 6 here, minus 1, choose 6. And that gives us the answer 9, choose 6, which would also, once again, be consistent with stars and bars. So, moving on, we're going to cover the roots of unity filter. This is a big term, but it might seem a little bit complicated, but you'll understand it as you go. So the roots of unity filter was covered in CNCM's very first lecture, which is on our website. We'll cover it again here, as it is a very powerful tool when used with generalizing functions. So the filter gives us the sum of the coefficients of every x to the n such that n is divisible by k. So let's say we had like a polynomial and k was equal to 3. That means we could find the sum of the coefficients of x cubed, x to the sixth, x to the ninth, and so on, instead of just finding them one by one. This sum can be expressed as this formula right here. Let me just erase this stuff. This is the roots of unity filter, and the formula can be expressed as p of 1 plus p of omega squared and so on over k, where, well, p of x is the generating function we have, and omega, 1, omega squared are all the kth roots of unity. The above computation might seem a bit ugly, and to actually do this computation, you need to be a bit familiar with complex numbers. You can educate yourself on complex numbers with CNCM's lectures on our YouTube channel, but if you don't need to, the above computation might seem a bit ugly, but in most cases, problems are designed such that the computation will reduce with the basic facts about the roots of unity. That is, 1 plus w squared, well, omega plus omega squared, and so on to omega to the k minus 1, basically the sum of all the roots of unity except omega to the kth power, is equal to 0, and omega to the kth power itself was equal to 1. This can reduce your computation greatly. So we'll cover a basic example to show this in action. So, how many ways are there to roll 3 standard dice such that the sum of the numbers that come up is divisible by 3? Well, our first goal here should be to come up with a generating function. Then we can use the roots of unity filter with k equals 3 to solve this problem. So the generating function is as follows. We already know that the dice roll generating function. We covered it earlier. Now there's no 160 because this is just covering the number of ways, so we're not considering probability in this. So this is just the generating function for a dice cubed. We know that we can find the number of ways to roll a sum of k by finding the coefficient of x to the k. We can expand this and find the sum of the coefficients of every single exponent divisible by 3, as I said earlier, but we can use the roots of unity filter to save a lot of time in computation. So moving on here, we have the generating function, and we want to use the filter for k equals 3. We just need to compute the following here. We have the generating function, p of x equals our dice generating function cubed, because there's 3 dice, and we have the term we want to find. This is the root of unity filter for k equals 3. P of 1 plus p of omega plus p of omega squared over 3. So to calculate this, we have the following. P of 1 is equal to 6 cubed is equal to 216. It's fairly easy. They just all become 1s here. Like in this generating function, not this one, they just all become 1s. So that's 6 cubed equals 216. P of omega ends up being this, w plus w squared plus w cubed plus w to the 4th plus w to the 5 plus w to the 6th omega. And if you simplify this with the fact that omega cubed equals 1 for the third roots of unity, then you get omega plus omega squared plus 1 plus omega squared plus 1. And as we said, those are 0. This here is 0, and this also here is 0. So we get 0 plus 0 cubed, which is equal to 0. Similarly here, the same thing happens. Once we simplify it down, we see that we just have 0 up here again, so we have 0 plus 0 cubed. And by the roots of unity filter, thus our answer is p of 1 plus p of omega squared, which is 216 plus 0 over 3, which is 72 ways to roll a sum that is divisible by 3 on 3 standard dice. And we will cover our final example in today's lecture, and this is the final problem we'll be covering. And this is a 2018 Amy 1 number 12, so it is pretty hard. For every subset T of U equals 1, 2, 3, all the way to 18, let S of T be the sum of the elements of T with S of the empty set defined to be 0. If T is chosen at random among all subsets of U, the probability that S of T is divisible by 3 is m over n, where m and n are relatively prime positive integers. So if you want to find a generating function for a subset T, this is fairly easy. We're going to find the generating function for S of t, the sum. So, taking a look at each of these elements, we can use the argument that for a subset, either one of these elements we pick is either in or it's out of the subset. And that's true for every subset. That's how you get, since there's 2 possibilities for each number, there's 2 of the 18 subsets for this set U. Using that same logic, well, if you want a variable to count towards, well, if you want a number to count towards our sum, we can express it as x to the k. If we don't want it to count towards our sum, we can just express it as 1, since that does nothing. So, we can write 1 as 1 plus x. So that is considering if 1 will appear or not. The 1 here is to say that 1 will not appear in the subset, and the x is that 1 will appear in the subset, as that x will contribute its exponent towards the sum. As we keep on going here, we have 1 plus x squared to account for 2, and all the way to 1 plus x to the 18th. So this is our generating function. And now we want to find the probability that s of t is divisible by 3. So we want to find all the variables x that have exponent divisible by 3. And that's where the roots of unity filter comes in. So we need to evaluate p of 1 plus p of omega plus p of omega squared over 3. Well, let's look at p of 1. P of 1 just makes all of these 1. So this is 2 right here, this is 2, this is 2, and there's 18 of these terms. So P of 1 is equal to 2 to the 18th power. P of W is equal to 1 plus omega, 1 plus omega squared, and then we get 1 plus omega cubed, which is, since omega cubed is 1, since it's the third root of unity, that's just 2. But, as you can see, since omega cubed equals 1, this ends up just being a recurring cycle all over again, 6 times. So this is just taken to the 6th power. So you want to expand this, and I'll just expand it here for simplicity. This is just w cubed plus w squared plus w plus 1. And we know that this ends up being 0, and this ends up being 1. So indeed, we're actually just finding 1 times 2 to the 6th, which is 2 to the 6th. And the same thing happens for p of omega squared. If you don't believe me, you can try it out, but the same thing happens for p of omega squared as well. So now we have our values. Moving on. So by the roots of unity filter, the number of ways we can pick subsets that have their sum divisible by 3 is 2 to the 18th plus 2 to the 6th plus 2 to the 6th over 3. But to calculate the probability, we need to divide this by the total number of ways to pick subsets, which is 2 to the 18th, as I said earlier. So we have this number. We can factor out a 2 to the 6th here, and so we can divide both the top and bottom by 2 to the 6th to get 2 to the 12th plus 1 plus 1 all over 3 times 2 to the 12th. So let's just calculate that numerator up there since the problem actually just asks for the numerator, m. So 2 to the 12th is 4096 plus 1 is 4098. So 4098 over 3 times 2 to the 12th. 4098 is actually divisible by 3. So that actually gives us that 4098 divided by 3, that is equal to 1366 over 2 to the 12th. However, we can simplify this fraction further since there is obviously the numerator is divisible by 2, so this becomes 683 over 2 to the 11th. The top is odd, the bottom is the power of 2, so this is the simplest form. And since the problem just wants the numerator, the answer is just 683. And that's it. So if you enjoyed this lecture, thank you for watching. Please do like and subscribe. And if you do want to join our Discord server, which has 1,000 members, if you need help with any math problems, any content covered in this lecture, there's a lot of people that'll be willing to help you. We have a great community over there. And that's all I have to say. And that link will be in the description below for the Discord. Thank you for watching.